So, first of all, welcome to the second session of the MLT series. We have, if you missed the first session, I have sent you the recording in the chat box. I have also painted that. You can take it from there. Okay. Okay, Kshitij, you can
Yeah.
carry on now.
Okay, let's start. Okay. Yeah. So in last session, we covered, we started representation learning, and before that, we covered the initial part, introductory part of MLT as well. Okay. Yeah. So today, we will finish the week one theory. Okay. And yeah, so the goal for, and one important thing is that today class won't be 2 hours, okay? It will be just 1 hour 30, around 1 hour 30 minutes, okay? Yeah. So yeah, as you can see my screen, goal for today is motivation to representation learning, motivation of representation learning. What's the need? Okay, what's the problem we want to solve? After that, we will cover the approach for the problem we have in hand. Okay, and then we will conclude and end the session with principal component analysis. Basically, this second section, here we will discuss how we develop principal component analysis algorithm. Okay, so is that clear with everyone? Hello, shall we?
Yes, sir.
Okay, yeah, guys, as I'll be on the other screen, so please feel free to mute in between and ask whatever doubt you guys have. Okay, yeah. Okay, so let's start. Okay.
And one thing also, if you have general query, you can post it in the chat box. I will answer it.
Okay. So yeah, so whatever we'll do today, first of all, we'll start with the revision of last session. Okay, we started the representation learning in last session, so we will revise that. Okay, and then we'll continue our discussion. So no problem if you weren't there in the yesterday's session, or I mean the last session. Okay, we'll cover everything. Okay, so let's start with the motivation of representation learning. Okay, so given a data set, what we want to do? Okay, we want to do two things. Okay, we want to compress the data. We want to extract a compressed representation of data, and we want to learn something useful from the data. Okay, so these are our two goals. We'll be working on these two things in this section. Okay, I mean in representation learning. Okay, yeah. So input in input we will have data set. Okay, so all these are vectors belonging to R3. Okay, so this is our input, and whatever algorithm we'll develop will give you compressed representation of this data. Okay, you can say it will give you compressed data. So let's start with this. Okay, let's start thinking about this problem and how we can solve it. Okay, so first approach is that let's say we have this data set. Okay, so yeah, let's say each number to store takes 1 unit of memory. Okay, so how many units of memory this whole data will take to store? 8 units of memory, right? Okay, so what can we do? How can we compress it? Okay, so as you can see, all the data points here lie on a straight line. Okay, so if this is the case, that all data points lie on a straight line, so what we can do, we can choose any vector along the line. Okay, along the line, and that will be our representative. Okay, and after that, what we can do, we can get to all the points in the data set if we have coefficients. So as you know, there is a vector which is representative for this line. Okay, so to get to the original points, we will have scalars. Okay, so if you multiply this vector with some scalar, you can get back to all the points. Okay, some scalar for this, different one for this, different one for this, and different one for this. Okay, and they are called coefficients. So as you can see here, if we have taken this vector as representative. So these are the uh, coefficients to get back to the original data set. Okay. And one important thing is that any vector along the line can be taken as representative except the zero vector. Okay. And using this method, we will be able to represent the, or we'll be able to reconstruct our original data set by multiplying the vector which with each scalar. Okay. So let's see how helpful is this. Okay. So originally the unit of memory required was d into n. How d into n? Because d is the dimension in which your data is, and n is the number of data points. Okay. So is it clear why it is d into n? Here the data is in R2 and you have 4 points. So 4 into 2 equal to 8. That is 8 points you have, right? Not 8 points. I mean 8 numbers you have to store. Yeah, simple. Okay, now with this method of representation, we just have to store d. We just need d plus 1 units of memory. And how is that? Because this is an RD. Let's say this is an RD. So you need d units of memory to store the representative vector, and as you have to store one scalar for each data point. So given that you have n data points, you will store n scalars. So n comes from coefficient and d comes from representative. Okay, so that's why you have d plus n units of memory required to store this compressed version. So is this clear?
Yes, bye.
Okay. So what's the problem with this method? The problem is that the real world data is not this simple. Okay. In almost all the cases, the data will be not this simple. Okay. It will not be in a straight line. Okay. So what we can do now? So let's take one example for this. Okay. Let's say this is okay. Let's say there is some point outside here. Okay, in our data set, there is some point over here. So in that case, what can we do? Okay, so one quick solution is that, okay, we are in R2. So to span all the vectors in R2, what we can do, we can take representative any two vector in R2, and for each data point in for each data point in our set, what we will do, we will store a pair of coefficient for each point. Okay, so to reconstruct x3, let's say we have some x3 here. What we will do, so this, yeah, this is the pair for x3. Yeah, you will multiply 10 with the 1 0 and 10 with 0 1 to get back to the original data point. Okay, but is this even helpful? Because look how many unit of memory we require here. So 4 for this, and how many for this? 8 for this, right? Not 8, my bad. Yeah, we have 5 data points. So this will be 10 units and this will be 4 units. Okay, this is not a good method, right? Because to store the original data we require even less memory. Okay, so this is not a good method. There is no compression happening here. Okay, so is this clear why this is a bad idea?
Yes, bye.
Yes, no, yeah. So now what can we do? Okay, so let's take one example. Let's say we have one data point outside the line. Okay, now whatever representative we take, it will be on the, obviously it will be on the line, and we can always take a representative such that its norm square is equal to 1, its length is 1 unit. Okay, so what can we do now? Okay, so the idea is that we will find a point on the line which is similar to this point. Okay, so how can we do that? So the idea is that the point on the line closest to our data point will capture most information of the original data point. Okay, so now what we have to find? We have to find a point on the line which has least distance from this point. Okay, maybe it is here, here, or here. We don't know. Okay, so this is the point which is outside the line. Okay, I mean this is the vector. Here I'm using word point and vector interchangeably to don't get confused. And this is the representative vector W. Okay, and the norm of W is 5. We can always choose a norm such that we can always choose a vector such that the norm is equal to 1. Okay, so now what we have to do? We have to find a replacement for our original data point. Okay, but now the question is how we will do that. Okay, yeah, so here I have written the all the things so you can read. Okay, the same thing which I just said. Yeah, so we want to find a replacement. Okay, so what you'll do now, let's say there is some point. Okay, it may be here, here, here. We don't know where it is. Okay, but whatever the point is will be some scalar times the vector, right? Will be some scalar times the representative vector. Is that clear? Why? Yes, no. Okay, that will be some scalar times the representative. That's clear. Okay, so now what's the difference? I mean, we want to find a point closest to the original point on the line. Okay, so the difference we want to minimize, whatever the difference between the actual point
Pandeyji,
and the
sorry,
proxy.
sir. From the
Yes.
previous thing to this connection, I'm not getting like, what is this line which you have drawn apart from the axis which is going through the, I mean, long line, no, like uh,
Yes,
W,
this line, right?
that line. It's a,
Okay.
as of now, it is some line, no, it is not defined yet.
Yes, that's why we have taken a vector, right? W. We don't know the value of W.
Okay.
So let's say there is only one point outside all the points are on the line, and there is only one point outside the line. Okay.
No, I couldn't get. What is that? All the points?
Let's imagine for now, all the data points except one data point lie on a straight line passing through
Okay,
origin.
which is it? Okay, okay. Now you got.
This
So
is our
So,
assumption for now.
except
excuse
one
me,
point,
sir.
all points are lying in this line, and that X is not lying on that line.
Yes.
Point X is not in the that line. Okay, please continue, sir. Sorry.
Okay, just a second. So, this line is a representative line for all other points except that one particular X point, right?
No. The okay. Okay. I'll
Like
just.
this line is a representative for all the other set of points other than the X.
Okay, this will get more clear. Okay, so this is some arbitrary line. Okay, I have just drawn it randomly. Okay, there will be some line, some best fit line. Okay, that we have arbitrarily drawn. Okay, for now. So
Okay, okay,
for
okay, got it.
what are we trying to learn here? We are trying to learn the case where data points, all the data points are not on a straight line. Okay, how do we deal with that scenario? So to understand that, we have taken a simple toy example that point is outside one point is outside some straight line. Okay, every other point is on a straight line. We don't know what that straight line is. Okay, we just have data points with us.
Okay, okay.
Okay, yeah. So we are saying there will be some vectors that will span that line, right? That is whatever the vector is, we don't know yet. Okay,
All right,
is
all
there
right.
any? Okay, yeah. Okay, so now what we want to do, we want to minimize, we want to find a point on the number line, sorry, not on the number line, my bad. we want to find a point on the line such that the difference between the actual point and the proxy, the replacement of this point on the line, we will call that proxy. Okay, so the proxy for the point, the difference between actual point and the proxy of the point is minimum. Okay, and we just concluded that whatever the point is, that will be some c times our representative vector. Okay, so now what's the difference between our actual point and the proxy? Okay, so the difference will be this. So this is the actual point and this is the proxy. And proxy, as we know, proxy will be this, some c times the representative vector. Okay, so just the same thing, nothing new. Yeah, so this is our uh, difference between actual point and the proxy. Okay, now we want this difference to be as small as possible. Why is that? Because as small the difference is, better the representative. My bad, not representative. Better the replacement point, right? Better the proxy is. So, I mean, I'll just show you here. So this point right here, wait a second. Yeah, this point right here is not good proxy for this point, right? Because this is too far from it. Whereas this, compared to that, this point is a better proxy. Okay, and this point is even a better proxy than that also. Okay, so we want to find what point is the best proxy. So yeah, this is the setup of problem. So we want to minimize the length of error vector. So to solve the problem, we'll state what this. So this will be your error vector. Okay, as we know, the closest point on the line passing through this point will be this foot of the perpendicular, obviously, right? So we want to find this point. Okay, so this we will call error vector for solving the problem. So this is your error vector. Yes, somebody has raised hand.
And this vector is basically the projection of the original on the representative line.
No, this is not, this vector is not projection. This will be the projection, right? We'll conclude that.
This will okay. This will
Yeah, we'll come on that point. Yes. Now we want to minimize this. Okay, this is your error vector. So we want to minimize the norm, right? The norm square here. So we know the formula for finding norm. So just this is the formula. Now we want to minimize this. Let's say this is FW. Okay, so just nothing new, just differentiate it, equate it to 0, find the value of optimal C. Because what is not in our hand here? Okay, because whatever W we take, that will have norm 1, that we know. So the, let's say W we know, W will figure out the only thing that will be different for all the points outside the line will be C, right? That C, that will be multiplied with the representative vector to get proxy. Okay, so now we will differentiate this obviously with respect to C. We want to find that optimal C. So we have just differentiated it, equated it to 0 and calculated the optimal C. Okay, and it turns out to be nothing but this value, and which is nothing but X transpose W divided by norm square of W. And we know that we have taken W such that its norm square is equal to 1. Okay, so the optimal C is nothing but dot product of X with W. Okay, whatever the data point is, take dot product of the data point with the representative vector. Okay, so this is nothing but a projection. Okay, projection of the vector on line, as someone said. Okay, sorry, I don't, I mean, I didn't pay attention to the name, my bad. Yeah. Now, okay, now we know for any data point outside what we have to do. So C, we will find like this. Okay, so once you know C, you can find the vector. Simply multiply this with W to get the proxy. You'll get the proxy. Okay, so now we know how to deal with the case where point is, we have some points which are not on the line. So is it clear how to deal with situation where point is not on line? Is that clear? Yeah. So now let's come to our problem. Okay. So obviously in real case, the data will never be like that. Okay. The data will never be on a straight line. The data will be very, you can say very random, very data will be like this. Okay. So what's the goal now? So we have to find a line such that, yeah, so one thing before that, one thing to mention, yeah, so we don't know, in our case we just have data points, and data points are like this. Okay, so we don't have any line. So what we have to do, we have to find a line such that the error for all the data points is minimum. Okay, we have to find the best fit line. So what's the problem here? We have to find best fit line for which net difference between actual data point and proxy is minimum for all data points. So is the problem clear? Is the problem clear? What is the problem in hand?
Repeat by.
So what you have, so in real scenario, the data we will have will not be this simple. It will not be on a straight line. The data we will have will not fit any line. Okay, like by that I mean it will not lie on a single line. The data will be like this. Okay, very random, you can say, in nature, not following any function, you can say. Yeah. Okay, data will be like this.
Okay.
So now what is our problem in hand? Okay, we have to find a line such that the difference between actual point and the proxy we are taking is minimum for all the points. Okay, so
Okay.
yeah, here I have stated the problem. Find the best fit line for which net difference between actual and the proxy is minimum for all data points. Is that clear?
Yes, sir.
Okay, yeah, just a second. Just a second. Yeah, sorry. Now let's continue our discussion. Okay. Yeah, we'll come on that as well. Okay, don't worry. We will take example of actual data set. Okay, toy examples. Yeah, understand how we do compression. What's the compression here? Yeah. So now, yeah, this is the problem in hand. So we'll have data set. Okay, and whatever, I mean, we want to minimize the error. Okay, the difference we are calling error. Okay, so we'll have some ideal line data set and we want to minimize the error. Okay, sum of error. So yeah, so this is the error. Okay, the length is error here. Okay, The magnitude of length here is the error. So we want to minimize the sum of error for each point. Okay. Yeah. So we'll take summation for all the point and we want to minimize this vector's length. So what is this? This is actual point minus this is the C, right? C, we calculated that, okay, it is X transpose W, and again multiplied with W to get the proxy. So this is your proxy, this is your actual point, subtract the two, okay, to get the error vector for each data point. Okay, we are we want to minimize this. Obviously it's error, we want to minimize this. Okay, now simply it is written length, so we have just written norm square here. Now we'll do some change and you will understand why we have done this thing. Instead of calculating the sum square error, we'll calculate average square error. Okay, and we'll try to minimize this. Now we know the formula of norm, right? So norm of W is equal to W transpose W. That formula we are using here. So norm of this quantity is transpose of it multiplied with itself. Okay, so now just do simplification, multiply this W inside. Okay, we already did this calculation yesterday. Yeah, this is simplification only, and note that here norm square of W is equal to 1. Okay, so on simplification we will get this function. Okay, we want to minimize this. So just pay attention here. We want to minimize this function. This quantity depends on the data set, and this W here is in our hand. Okay, only this W is in our hand. Let me write I here. Yeah, this is the I. So this W is in our hand. So when you want to minimize this entire quantity, that means you want to, I mean, this you can leave because this is not in your hand. You can only do something with this. Okay, so this quantity we want to minimize. If you minimize this quantity, that will automatically minimize this. Okay, so the W which will minimize this quantity, negative of this, will minimize the entire quantity. Okay, so the equivalently you can minimize for W such that norm square of W is equal to 1. You can minimize this function. Okay, yeah, we have removed this. And now pay attention, this is negative, right? So if you remove the negative, this is equivalent to a problem, optimization problem, maximize for W such that norm square of W is equal to 1, and this is the function. Okay, now little manipulation here. So this is square, so we'll simply write it in this way, multiply it. Okay, just little bit of simplification. And now note one important thing here is that this matrix right here, okay, yeah, first of all we have to bring this inside. That the reason why we are dealing with average error is that this quantity right here, so this is a matrix and this entire quantity is covariance matrix. Okay, and we'll talk about covariance matrix, what a covariance matrix is. Okay, so this matrix here is familiar to us. Okay, so now the equivalent problem is that, okay, this is covariance matrix which is represented by C. So equivalently we can maximize for W such that norm square of W is equal to 1. We can minimize this quantity, W transpose CW, okay, where C is equal to this. And turns out we already know solution for this problem. Okay, so the solution is W is the eigenvalue corresponding, sorry, W is the eigenvector corresponding to the largest eigenvalue of C. Okay, we'll talk about what a covariance matrix is and what eigenvalue eigenvector is. Okay, what these terms are. So first of all, let's talk about covariance matrix for those who have not done MLF. So let's say we have three vectors. So the covariance matrix is nothing but this. So we calculate the variance between, we calculate the variance of each data point, and we calculate a covariance of each pair. Basically, for any ij point here, so let's say for any Cij, so any Cij in the matrix, it is nothing but variance of, sorry, not variance, covariance of, let's say all these are xi's. Okay, this is x1, this is x2, this is x3 for now. Okay, this is covariance of xi and xj. Okay, so this is your covariance matrix. All the elements are nothing but covariance of each pair. So that's why here, so what is this actually? This is covariance of x1 with x1. So it is variance. Okay, similarly, this is the matrix. So is the idea of covariance matrix clear? Hello? Is it clear?
Yes, bhai.
Okay, now let's talk about eigenvalue of C. So what is eigenvalue, eigenvector? So we already know about linear transformations, right? So let's say there is some matrix C and some vector, and the transformation we get on multiplying C with W1 is such that only the uh, only the norm changes. So the transformation is such that, let's say this is the original vector, this is only scaled. Okay, this is your transformation. That is, nature of transformation is such that when you multiply vector with the matrix, the resulted vector is some scalar times the original vector. The direction is not changed. Okay, is that clear? So whatever vector you have, okay, so this is a special vector which behaves this way, and it is called eigenvector, and the scalar here is called eigenvalue. So is eigenvalue, eigenvector clear? Is it clear? Hello?
Yes, bhai.
Yes. So now how it is related, and first of all, let's say we have a method of finding, we for those who have not completed MLF, we have a method. Given a matrix, we can find its eigenvalue and eigenvector. Okay, so that's not a problem for us. So now the thing is how this is related to our problem. Let's see. So here, what you do, what you have to do, just pre-multiply both on both sides, pre-multiply with W1 transpose of W1. So here, this quantity is a scalar, so you can take it out. And what is this? So this inside you will have W1 transpose W1, and we already know the norm of W1 is equal to 1. So this will be equal to lambda 1, which is the eigenvalue. Okay, so your eigenvalue is equal to this quantity. And what is the quantity? We are dealing with the optimization problem of this quantity only, right? So this is how your eigenvalue is related. Okay. So is it clear? Is the relation clear? Is the relation clear?
How did you get W1 transpose into lambda 1 W1 as lambda 1?
This right here, right?
Yeah.
Simply on both sides, pre-multiply with W1 transpose. So when you pre-multiply it, on the left hand side you get this, and on right hand side you will get this. The thing here is that this is a scalar. Lambda 1 is a scalar, so you can take that out, and and inside you will be left with W1 transpose W1, which is nothing but norm square of W1, correct? And we already know norm square is equal to 1.
Yes. Thank you, sir.
Okay. Yeah, and this is the problem we had in our hand, and these are the previous steps of the problem. Okay, so we have concluded this. Okay, so what are we learning here basically? Okay, we know that, okay, for best fit line, we had a problem for best fit line. We developed a method to find the solution for best fit line. But what are we learning here? Okay, where is the compression happening? Where is the learning happening? That's the big question, right? So any problem here as of now? Any doubt in what we have covered? Anyone? Okay. Yeah, if you have doubt, feel free to interrupt. Okay. Yeah, let's continue. So let's have geometric perspective of this. Okay. So I'll ask you guys a simple question. What is a coordinate system? And how it helps us, what it does? These are my questions. What is the coordinate system? Anyone?
You have two, I mean, XY coordinate, if it's a plane, XY coordinate, you can represent any point using those two coordinates. Like if it is an XY plane, X equal to something and Y equal to something, then you can pinpoint in that coordinate system, like in the plane.
Correct.
Similarly,
That's
3D
correct.
also, 3 dimension, you can take one more dimension, uh, three values. If you know, you can pinpoint the exact point
Correct.
in
Correct. That's
3D system.
yeah. Correct answer.
Then,
But what's the reason? Okay, let's dive deeper into it. Okay, let's see in a way we haven't seen it before. So let's say you have an XY coordinate system. Okay, and these are the points. So on the x-axis, what are you measuring? So whatever, leave the problem here. Okay, leave this for now. Just imagine you have coordinate system xy plane. So what do we measure? Okay, so x coordinate, uh, sorry, x-axis is used to measure one quantity, right? Let's say height. So let's say you don't have y-axis for now. You just have x-axis. So this will measure the height, the quantity height in our example. So let's say this is a 5, this is 8 unit, this is 9 unit, and so on. Okay, so it will measure one quantity, right? So your x-axis will measure one quantity. What about y-axis? Y-axis will measure another quantity. And okay, one question is that why are the axes perpendicular to each other? Why can't they have some theta degree? Why only 90 degree? That's the question. Okay. Anyone? Anyone?
They are independent of each other, sir.
Yes, they are. Better term would be they are correlated. And why is that? Let's see. So let's say we have this example of height, weight. Okay, and these are the points. Now, yeah, these are the not this example. Just a second. Yeah, I'm trying to explain how they are independent, or the better term is decorrelated. Yes. So now let's say the data is like this. Okay, for example, leave these for now. The data is like this. Okay, the data is like this. Okay, so now we want this is your data, and now we want to find best fit line. We want to find best fit line for these points. So Okay, so we have to find a line such that the error is minimum, right? So the best fit line will be this, will be y-axis, okay? And the proxies will be here only. So you have 2 points as proxy, okay? So now these 2 points are on the line only, right? So yeah, just a second. Okay, I'll explain this. Okay, we will understand why we need 90-degree. Okay, yeah. For now, maybe it's difficult to explain, but with the entire example, it will be clear. Okay, yes. Just a second. Let me explain this. Let me start the geometric perspective again. Right. Yeah. So the first thing we have to understand in the geometric perspective is the coordinate system. Okay, we have coordinate system to measure different quantities. Okay, talking about x-axis to 2D coordinate system. Okay, so both the axes measure different quantities and they are perpendicular because the two quantities are decorrelated. Okay, so now let's say this is the data we have uh, of height versus weight, and these are the data points. So when we find best fit line, what is actually happening? Okay, what this line represents now. So your height is on the x-axis. So x-axis is the best direction to measure the variance of height. There is no better direction than x-axis to measure the variance of height. Okay, so for this point this is the height, for this point this is the height, so this is the height, and let's say these are the different heights we have. So this is the best variance. Okay, in this direction the variance is best captured. Similarly, for y-axis we are using weight for y-axis. So y-axis is the best direction in which the variance of weight is captured. Okay, so for this point, this is the variance. For this point, this is the variance. For other points, let's say these are the these are the weights. Okay, so your y-axis is the best direction to capture the variance of weight. Okay, so is it clear why x-axis is best
No,
direction?
but sir, why, sir? Just because you written this as white and height, it is like axis you're capturing. But we don't know, no,
Ah,
which, unless we calculate, we don't know how it is going to calculate, capture the best variances. You have to find out, no?
no, no.
Because
For this, okay, we are now what we are doing here. We are defining our coordinate system, right? Our coordinate system is such that the x-axis is for height and the y-axis is for weight. Okay, so we have defined the coordinate system that way. Okay, so obviously for any point here, for all the points, the best direction that captures variance of height is x-axis, and the best direction to capture the variance of weight is y-axis.
okay, yeah, but one dumb question. So if you take the variances along the height axis for the weight, what will be the variance? It will be zero or maximum. How it is
Yes,
happening?
it will be zero. No, in not in this case. Let me come there. Okay. For now, just we are just talking about when you have a coordinate system where x-axis is measuring x-axis is used to measure height and y-axis is used to measure weight. In that case, the x-axis is the best direction in which you can capture the variance of height only, not weight. Okay, no relation with weight. So this direction is best for capturing variance of height, whereas your y-axis is the best direction to capture variance of weight. Okay, let me finish. It will be more clear. So what are we doing when we are finding best fit line for the data points? In a way, we are finding the best direction to capture the combined variance for height and weight. Okay, so x-axis is the best direction that measures the variance of height. Y-axis is the best direction that measures the variance of weight, and the best fit line is the best direction that measures the combined variance of height and weight. Is it clear? Any doubt here? Any doubt on how height is, sorry, how x-axis is measuring? Sorry, any doubt on how x-axis is the best direction to measure the variance of height? Is there any doubt on how your best fit line is the best direction that captures combined variance of height and weight? Is there any doubt?
We don't have a doubt, but still the concept is little high. Maybe as we proceed, maybe I can understand.
Yeah. So, okay, I'll try to explain it out. Okay. So, what these data points represent, let's talk about this data point. Okay. So, this will have some x value, right? Let's say 5, and y value is 2. So, when we talk about the points here, okay, so this point measures the height, right? I mean, if you just take this point, so this point has same value of height as this, right? And same for all the points. Okay, so here you will have points measuring the height of your data set, right?
Yes.
So if you take projection of all the points on x-axis, it will give you points measuring the height, right, of each data point. Correct?
Yeah.
And as this is the axis we have defined for height, this is the best direction that measures the variance of height. Okay, because this is the actual axis, right? This point right here represents what is the sole purpose of this point. This point is nothing but, let's say, this represents 5 units of height, right? And this is let's say 10 units of height. But when you talk about this point, this point is representing two things, right? Some unit of height and some unit of weight. Okay.
True.
But
Yes.
this point is only for height and this point is only for weight. Okay. There is if you talk about the amount of information they give. Okay, so these data points give you information about height and weight. But whereas when we take proxies, okay, so they lose some information, right? They lose some information because you're not taking the original point, so there will be loss of information. Correct?
Yes.
Okay. Now let's say we just want to we want to let's say, okay, this is our original data set and we want to do, I mean, this may sound funny, we want to do opposite of compression, right? Let's say we want to double the size of storage. Okay, in that case what we can do, we can project all the points on x-axis, project all the points on the y-axis, and the points we get on x-axis will represent different heights, and the points we get on y-axis will represent different weights. Correct? And on combine and with that, with help of the points, let's say this is the point projection, this is the projection for this point, and this is the projection for this point. If you add these two, you will get back the original, right? If you add these two vectors. Correct? So in a way, you are with this method, with this, you are doing opposite of compression, right? But when we just talk about the projections on x-axis, all the points will only contain information about height, right, and nothing else. So that's why the x-axis is the best direction to represent best direction that captures most of the variance of height, because the sole purpose of the axis is to represent height, right, to be scale for height. I mean, I guess this will take time to digest, but as of now, from here, we have to conclude that, okay, whenever we are in any coordinate system, whatever whatever quantities we are measuring, let's say height, weight, so the axis for height will be the best direction to measure the variance of height. The y-axis, which is for weight, is the best direction to measure variance of weight. Whereas the best fit line we have, is the best direction to measure the combined variance. Yeah, is this clear? Yes, no? Okay, I'll be back in a minute. Just a second. Yeah. Any doubt so far? Okay. Yes. So the thing is, let's talk about this point, okay, which is not on a line. So when we take proxy of any point, in place of the actual data point, we are storing the proxy. So there will be loss of information, right? This quantity, we said this is error, but this is actually, we are losing information, right? Is that clear? Why we are losing information? Because we are not storing the actual data point, we are storing the closest point to it on the line. Okay, I mean, as simple as that, because we are not storing the actual data point, we are storing a best representative of the data point. Okay, best replacement. So there will be a loss of information. Is this clear?
Yes.
So now, what can we do? How can we capture this loss? I mean, how we want to capture what we have lost, right? Okay. So what can we do now? Okay. So yes. So let's get back to our height weight example. Okay. These are the data points. This is the best fit line. Okay. And let's say this is the equation of line. Okay. So the line is this: height plus weight divided by √2. Yeah, someone raised hand.
Why we want to capture what is the data lost? Because actually we have find out the line where we have the minimum error. Now, what is the reason we want to find out what is the quantum of the error? We have already found
Yes.
the best fit line.
Yes. So the thing is, now what we are doing, we are not storing the actual data point. We are storing proxies. Okay. So there is loss of information, right? What our actual data wanted to convey, 90% of that will be captured in the proxies. Okay. We want to know what our actual data wanted to convey. Okay. There is loss of information. we want to, when we are reconstructing the, what's the purpose here? To compress the data. Okay, that's the first purpose. And the second purpose is to learn something. So when, why do we recompress? To use less memory. And whenever required, we can go back to the original data point, or we can go back to data point close to the original data point, right? As close as possible. So the difference between the actual data point and the data point which we that we can go back to must be minimum. Okay, let's say we had data point 2, 2, and we compressed the data, we stored it in some way. Now we want to uh, go back to the original data point. So the goal is, I mean, in ideal case, you should be able to go back to the original data point, but that's not possible in this case. So you will go as close as possible to the original data point, because you don't want to lose the information. The information is important.
Okay, okay. Got it.
Okay, now let's say this is the data point, this is the best fit line for the data point, and this is the equation of line. Okay, so now we can do one thing. So this is the line that captures best, and this is the line that captures this is the line capturing the best combined variance, or let me just give me a second. Yeah, so this line represents the best direction in which the combined variance of height and weight can be captured. Okay, so now let's do one thing. Right now we are in coordinate system of height, weight. This is the coordinate this is the coordinate system we have. Let's make this x-axis. Let's rotate this, let's forget these two axes, and let's make this your x-axis. Okay, so when we do that, now this becomes your x-axis. Okay, and the perpendicular axis will be this. Okay, so what we want to do now, what's the purpose of this? Okay, so the thing is, these are the original vectors. But when we are considering this as your x-axis, we are changing the data point. Let's change we are just changing the point of view, right? Nothing else. So we are changing the reference point. We are making this x-axis. So all the data points will change now. So their value will be with respect to this axis. The x value will be with respect to this axis now. So that's why, wait a second, why it's not, let me fix this. Okay, just a second. Yeah, so now, yeah, where were we? So this data, yeah, so this we will treat now as x-axis, and according to that, now each data point's value will change. Now the question is, what are they representing? Okay, now let's look what they are representing. So we talked about error, right? We talked about this error. Okay, so what we will do, on the original data, we performed our algorithm and got a best fit line. Now in the error, and what is the error vector? Let's go back here. Yeah, this is the error vector. Okay, so we will have a lot of error vectors, right? For all the points, we will have error vectors. So now we will make data set of error vectors, because they are important for us right now, because they contain information. Okay, they contain information, they are important to us. So now what we will do, we will. So these are the vectors, these theta vectors. Sorry, these vectors, these error vectors are, I mean, here the magnitude is represented here, right? But as you know that, yeah, as you know, this is the magnitude of vector, okay? But where is the vector? It is not in, I mean, you can say it is here, but actually it is not in this world, because all the vectors are, all the vectors start from the origin. So the error vector, let's say this is the point, and on changing the axis, okay, now when we make this x-axis, the point comes here. So the error vector is this. So these points are nothing but they are error vectors. Okay, these are your error vectors in the coordinate system, in this coordinate system. Okay, where your x-axis represents this and y-axis represents this. Okay, now you have the data point. Now again, what you will do, you will find best fit line for these data points to capture information out of them. Okay.
So, sir, the y-axis is minus height plus weight by root 2.
Yes, because it will be perpendicular, right?
Hmm.
So the equation perpendicular to this will be minus multiply it with minus, right? It will be minus height plus weight. Okay. So let's say for any vector here, it is 1 unit of height plus 1 unit of weight divided by root 2. So vector perpendicular to it will be this, right? In that case, when you will take dot product, the value will be 0. Correct? Is it clear now? Just take the dot product of 2. You will understand why these are the values.
Okay, sir. Okay, sir.
Wait a second. Wait a second. Okay, let's just leave the dot product part. Maybe that's not correct. Yeah.
So if you
Okay,
go to the previous, if you go to the previous diagram up, yeah, here. So this is the error vector in yellow, right? So this error vector
Yeah.
can be moved to the origin, right? It is the length of this error vector will be the same as a parallel vector which starts on the origin, right?
Yes. Correct.
Yeah.
Correct.
So then, how do you say that if when it is projected on the those data points should actually be perpendicular to this to the best fit line, right?
No,
Error
data
vec-
points
The error vector should be perpendicular to the best fit line, correct?
are perpendicular, right? Okay, just move it to origin. It is perpendicular, and when you will move all the data, all the vectors, they will form a line here. Okay.
Yes.
Yeah, that's one perspective. Yeah, I wanted to show you a different perspective of it. Okay, this one. When we go in this coordinate system. Okay.
Okay, sir. Okay.
Okay, so when we go to this coordinate system, all the points here are the error vectors. Now we again find best fit line for this. The best fit line for this will be y-axis in this coordinate system. Okay. And why is that? Because what we want to find, we want to find a line with minimum error, right? And this will be the line with minimum error vector. Is that clear? Yeah, is that clear?
So can you explain once more?
Yeah. So now, yeah. Okay. Yeah, I mean, with this data point, so we are just running the same approach. We are doing the same approach. The points that I have represented may not be very accurate. Okay, but the points will be such that the best fit line will be y-axis, because we want to reduce the error, right? Is that clear? Hello.
No, sir. Can you please explain once again?
The best fit line is the x-axis, no? And the y-axis is perpendicular to x-axis.
Just a second. Yeah. Okay, this may not be data may not be. Leave this. I'll show you the other perspective here. Yeah. So all these error vectors. Yeah. Listen. Leave that part. All these error vectors we have. Just move it to origin. Okay. So all the error vectors will line up. Okay. All the error vectors will line up, and now the best fit line for them will be just the line passing through them. Okay, right? All the vectors will be on straight line, on the same line. So now you find best fit line for them to capture the information lost. Okay. Yeah, for this part I'll get back to you guys on later for this. Okay, leave this for now. So is it clear how do we find information from the error vectors? So what you do, you line them up, right? Line them up, you shift them to origin. So then all the error vectors will line up, and the best fit line will be this, because all the error vectors are on same line. Okay, so that means this right here is the line represent capturing most of the variance of height and weight combined, whereas the line perpendicular to it captures rest of the variance. Is it clear?
Yes, sir.
Yeah. Anyone doubt here? Yes. Nikita? Anyone else? Okay. Yeah. So for now, yeah, let me conclude here. These are the data points. We find best fit line. This is the best fit line we get. Now, there is information we lose when we take proxy. Okay, there is loss of information. So what can we do? So now again run the same algorithm on the error vectors. Okay, when you shift all the error vectors to origin, they will line up. So the best fit line you can find for them now. So this W1 represents the direction that captures most of the, the direction that captures the combined variance of height and weight. Okay, it doesn't capture the full variance. Let's say this captures 80% of variance. Rest 20% will be captured by the best fit line for error vectors. Is it clear? Hello?
Yes, sir.
Okay, so now let's look what we are doing. So we have data set, okay, and we assume it is centered, and I'll come on what is centering and why it is required later. Okay, we find the best fit line, that is we find W. Then what we do, okay, after calculating W, now we have to capture the information we lose. Okay, so what we'll do, we'll find best fit line for error vectors. Okay, and as our data is in R2 here, so after that, okay, so after that, let's see what's happening. So all the data points are here, okay, on a straight line. Okay, so now there is, after this, if you will try to find best fit line, it won't make sense, right? The error will be 0. that because that's the line on which all the data points are, all the error vectors are. So after this, after doing the step for 2 times, on the third time, the vector will, the error is 0. I mean, after the second round of finding the best line, the error will be 0. Is that clear? Is that clear why the error will be 0 after 2 rounds?
No, why 2 rounds?
So in
Because
this
we
case,
are
one
having 2
round.
features.
Why 2 rounds? Okay. Our data is in R2, right?
Okay.
These are the data points. Okay, let's say this is the point. We use this as a proxy. This is the error vector. Similarly, there will be a lot of data points. So for all of them, we will line up the error vectors, and all of them will be on a straight line, right? Is that clear? All of them will be on a straight line.
Yeah.
So now there is a line from, okay, let me show you the first part. Yeah, in the case where all the data points were on a straight line, you were able to reconstruct the actual data point, right? So here the error is 0 in this case.
Yes.
So after 2 rounds, the error becomes 0 because data is in R2. And the reason why error becomes 0 is that all the error vector will line up. Okay. When we talk about, let's say, R6. So on the 6th round, when you on the after the 6th round, the error vectors will line up in R6. And in RD, on the after the dth round, the error vector will line up, and then the error vector, then the error will be 0. Is that clear?
So in this case, in the first round only, it is lining up, no, sir?
Okay, it is lining up after the first round. Okay, after the first round, when you get the error, they line up. So now after this, if you try to find the error, that the error will be 0, right? So we are talking about after. So in R2, we talk about after second round. So after second round, the error will be 0. After the first line, these are the error you have. Okay, and they line up after the first round. But after you find the best fit line, okay, that is after the round 2, the error becomes 0. After the first line, error is not 0. This is the error.
Okay.
Yeah, is it clear?
Yes, sir.
Any doubt, anyone? Yeah, okay, let's continue.
So this concept of second round is not clear. I'm not able to understand what do you mean by second round?
Okay, but let's talk about the first line when we have original data points. Okay, you have original data points. These are the vectors. Okay, now you find best fit line. This is the best
Yes,
fit
we
line.
find out that. Yes.
You will lose some error, right? You will have some error, right? What's the error?
Yes. Yes.
You
Yes.
have this for all the data points. What you do now, you want to capture the information you lose when you when you replace the point with the proxy. You want to capture this information. So what you can do, you can find the best fit line for error vectors. And what this is the error vector, right? Similarly, here you'll have error vector, here you'll have error vector here. So what you'll do, you'll line all the error vectors, line them up.
Perpendicular to the original best fit friend. Yes.
Yes, you will shift them, but you will parallelly shift. You can parallelly shift any vector, right, in this space. So you'll shift them, you'll bring them to origin. Okay. Now, now the points. Okay, these are the points that representing error vector. So all these points will fall on a straight line.
Yes.
Okay.
Yes.
Now, when you try to find best fit line, you will get this line. Okay. And
The same line we
the
will. Yes, yes.
and the error now. So what is the error? The difference between actual point and the proxy. But here, the actual point and proxy both are same, right?
Yes, on the same
This
line. Yes,
error,
on same. They are same.
yes. So yeah, so the error becomes 0. Correct.
Okay, okay, okay. Got it, got it.
That's why we say after round 2, the error will be 0. Yeah. Now let's extend this idea to RT. Yeah. So we have data set in RD. We find best fit line. Then what we do to capture the lost information, we find best fit line for the error vector. Okay. And as the data is in R3, the W2, that is the line perpendicular to W1, that will capture, let's say let's say the first W captures 80% of information. The second W captures, let's say 5% of information. So you will continue this to capture uh, all the information lost. What you will do, you will repeat this process of finding best fit line for error vector for D rounds. Okay, so this so when we find W1, this is the first round. When we find W2, that is error for the best fit line for error after round 1. Okay, so that gives you W2. Then after this, let's say, yeah, this is the error after first round. Okay, so now we are working on these data points. So this represents a data point. This is basically error vector. So you find best fit line for them now. Okay, after round 2, what happens? This is your new error vector. So basically there is nothing new. Treat this entire thing as vector x, then repeat the process. Okay, so this is nothing but x minus x transpose w2 w2. So this is your error now. If you simplify it, just this is nothing but simplification. You can take a look at this. An important thing is that w1 transpose w2 will be equal to 0 because they are perpendicular. Okay, now the error vector, now the residue is like this, x1 minus this and this. Okay, so after D rounds, what will happen? The residue will be equal to this xi minus xi transpose w1 into w1 and so on. Okay, so from this we conclude that xi is nothing but combination of scalar times wi's, w1 w2 to wd. Okay, so is this clear?
So how do you find the W1 first? It's an
Yeah,
approximation you said, no?
no, if you go back to this part, we already know the solution for this, right? This is nothing but the eigenvector corresponding to the highest eigenvalue.
Okay.
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 Now,
Sir, after each round we have to store the value. Huh?
so after each
we have
round,
to-
after each round, you have to again find the best fit line for error.
Sir, so after each round we have to store the value of the error and as well as the proxy point. Then how the
Okay,
data is compressing?
we'll get to that. We'll get to that. Don't worry. Yeah. So after D rounds, you conclude this. So xi is equal to this. Okay, and what is this? These are our W's, and this right here is xi transpose wi. Okay, so when the data lives, let's say data is in R3, but actually in R3 it lies in a linear subspace, some lower dimensional linear subspace. For example, let's say our data is such that after 3 rounds the residue becomes 0. That's the nature of data. So in that case, you just have to, so the xi will be equal to this, right? Xi transpose W1 into W1. Then xi transpose W2 into W2. Here we'll have W2 and then W3. So each data point can be represented as linear combination of W's, correct? Correct? Is this clear?
Yes.
So now we only have to store these three W's, W1, W2, W3. So it is in RD. So 3 points. So 3 times W. Sorry, 3 times D for storing this. And for each data point, we have to store scalar value. For each data point, this is the scalar we have to store. Correct? So this is different for, I mean, this is data specific, data point specific. So here you have to store three W's and 3 scalars for each data point. So originally the case was, let's say you have your data is in R100, you have n data points. So this is your memory storage, memory required. But now here you just have to store 3 vectors. These are the 3 vectors and they are in R100. So 3 times 100. And for each data point, you have to store 3 scalars. This is 3 times n. So in general, when your data is in some linear subspace in Rk, so the data actually is in Rd, but it lies in linear subspace of Rk. Okay, then the formula is this: d times k plus k times n. Yeah. So is it clear how compression is happening? Hello, is it clear?
Yes, wait.
Hello. Yes. Yeah. Now it is clear that compression is happening. And the next question is, what are we learning? Okay. So we are
Before going
learning.
there, Krishna bhai, एक minute. Before going to this, further continuing, so we said that W1 captures 80% of the variance and it is the best fit line. Okay. And after that, that becomes our x-axis and you are taking the error in the like perpendicular line where the error, you move it to the origin and that will be the reference for the new y. Okay. That is what we
Just a
said.
second. Yeah, just a second. Yeah, don't think of it as now for now. Don't go to the perspective of changing the axis. Just now, think of the perspective of aligning the error vector and finding the best fit line.
Okay, fine. Finally, if it is a like here in our case it is in R3 and hence we got W1, W2, W3, correct? So intermediate points, how the vector will look like because like do we have any software simulation which will take a set of data and try to tell us the best fit line and the best error fit line,
Okay.
something like that?
For that, we'll come back to you for that.
Okay,
Okay.
that's
At
fine.
the
Thank you.
moment, I don't
Thank you.
know
Thank you.
any
No
software
problem.
for that. Okay.
No problem.
Yeah.
Thank you.
Okay. So now we have concluded how compression is happening, and the last thing is what are we learning? So what are we learning with these W's? We are learning the direction in which there is most variance in the data. We are learning 3 directions that captures most of the variance of data. Okay. Yeah. So that's what we are learning. I wanted to cover other things as well, but yeah, unfortunately I have to leave now because literally I have a train to catch. Okay. Yeah, so we'll conclude the session for today. Okay. Yeah, we'll have next
No,
session
with
in
this,
few
how
days.
much we have covered? Have we covered 1.5 or how much more we have?
Yeah, we have covered more than that, I believe. Okay. Yeah, just
Okay.
this part is left. Okay,
Okay.
just stating this, just conclusion was left. Okay. Yeah, this
Okay.
will
Right.
cover in the next session. Okay, you can go through the notes. Okay,
Okay. That's fine.
I'll share the
Thank
notes
you.
in the chat as well as it will be shared. Okay.
Okay. Thank you. Bye.
Thank you, sir.
Yeah, I'm just sharing the notes, and after that we'll end the session.
Okay.
Yeah, I have shared the notes in the chat. Thanks for joining. We'll meet again in the next session.
Thank you.
Thank you, sir.
Thank you.